Okay, for your information, I have uploaded the latest lecture notes for this week, okay, in Google Classroom. Please go and download if you want to have a copy of the lecture notes, okay. You can refer to the lecture notes during the class. Okay, this week I will start another topic, okay. VLSI interconnects. Okay, the interconnects here means the wire. Okay, some of the characteristics of the wire will be mentioned, and then how the wire can affect the performance of the system also will be mentioned. Okay, so interconnects wire is used to connect components on a VLSI chip, and also to connect chips on a multi-chip module, and connect multi-chip modules on a system board. Okay, so let's have a look. Okay, what you all have to learn for this. Okay, this is the outline. Okay, the outline is on the wires on the chips. Okay, and also in the chips with wire, they are so-called these source drain resistance and contact resistance. Okay, and also other than resistance, they are capacitance. Okay, the capacitance here, they are wire capacitance, parallel plate capacitance, and fringing capacitance. And also there is a one effect, we call it as a skin effect. Okay, so what is skin effect? It will be discussed, okay, during the lecture class. Okay, so all these will be covered, okay, under this topic. Okay, as an introduction to this topic, okay, wires on chip. Okay, wires, okay, we know the wires can be formed in a form of layer, okay, in a physical design of a chip. Okay, in the real outlook, okay, this is the figure that you can see, the wires on the chips. Okay, this is how the wires looks like. Okay, so you see this is all wire, okay, connecting the chips, okay, to the metal layer. Okay, most of the chips is wires. Okay, um, most of the chip is covered by wires, and there are many layers of wires. Okay, so as already shown here, this is wire, and also this is wire as well. Okay, this is wire, this is the metal layer as the interconnect. Okay, they are with all the connections here for signal routing. Okay, all these in the chip, they are transistors. Okay, so transistor is important because they are like switches, and then they allow the chip, okay, to perform different function. Okay, and then the wire, okay, wire is also important. It's also as important as the transistor. Okay, and wire affects the speed, okay, the signal speed, and then the power. Okay, power here can be the power that uh, it dissipate, okay, and also the noise. Okay, when there is a signal propagate from one point to another point through the interconnect, okay, there will be some noise that will be induced, okay, from the coupling. Okay, and the wire, okay, they are arranged or can also run in orthogonality. Okay, this is refers to the alternating layers. Interconnects, okay, and interconnects is a thin firm wire that electrically connect two or more components in an integrated circuit. Interconnect can introduce parasitic components of capacitance, resistance, and inductance. Okay, parasitic. Okay, the term of parasitic here means unwanted. Uh, uh, is not desire. Okay, so this term you will see it oftenly. Okay, later when I discuss about the capacitance and resistance. Okay, this parasitics is quite an important elements that we have to look into so that it will not cause any degradations of the performance of the chip. Okay, so interconnects here, why it is important? Because interconnects can degrade, okay, the performance of the chip, okay, due to these parasitic components. Okay, parasitic components is caused by the capacitance resistance. Okay, later I will cover in more depth on the capacitance and resistance. Okay, these parasitics detrimentally affect the performance. Okay, performance here means the propagations delay. Okay, it will cause a large propagations delay. Okay, so if a system has large propagations delay means the performance is not that good. Okay, and also it will affect the power consumptions and reliability. As transistors are scaled down in size and the numbers of metals wiring layers increases, the impact of the interconnect parasitics increases. Okay, so there is a need to model the interconnects to evaluate their impact. Okay, so this one can be easily understood. Okay, now we have a very small transistor in a chip. Okay, so all the transistors need to be connected, okay, with the metal wire. Okay, so the more transistor in a smaller size means that the more numbers of wires that will be needed to connect them. Okay, so we will have to consider the increase of the numbers of layers in that chip. Will that affect the power consumptions and reliability of the chip? Okay, uh, why we have to consider because of these parasitics. Okay, it will increase. Okay, parasitics have multiple effects. Okay, multiple effects on the circuit behavior. An increase in propagations delay or equivalently a drop in performance, an impact on the energy dissipations and the power distributions. Okay, and introductions of extra noise source which affects the reliabilities of the circuit. Okay, so all these are the point that I mentioned for this one, for this. Okay, okay, so when we mentions about the reliability of the circuit, it is means that the parasitics will cause an extra noise. Okay, this extra noise will uh, affect the reliability of the circuit. Okay, wires and wires. This is a physical diagram of MOS transistor with metal layers. Okay, uh, so you can see that this is the MOS transistor. Okay, and then they are connected with the metal layer. Okay, metal layers can be of different level. Okay, level 1, level 2. Okay, level 1 normally we call a low level layer. Okay, method 2 is high level layer. Okay, this diagram shows a very simple diagram of a MOS transistor with the metal layers. Okay, the real MOS transistors on the chip, okay, they should actually look like this one. Okay, you see here there are many level, okay, and all the level here are with contact, okay, and also the interconnects. Okay, interconnects we can classify as local interconnects and global interconnects. Okay, and the layers, if you see here, the highest level of the layers, the thickness also will be larger. Okay, so the thickness are different. Okay, for low level layers and high level layers. Okay, this is a 2D wheel, okay, from side wheel. Okay, many layers of metal interconnects are possible. Okay, modern processors use 6 to 10 metal layers. Okay, examples Intel 180 nanometer process. Okay, this is the layers. Okay, it shows different layers have different thickness. Okay, you see M1, M2 until M6. Okay, it means the layers from low level layers to high level layers. Okay, the lower layers called as M1. Okay, so this is the low level layer. Okay, this is high level layer. Okay, for low level layer, you see here the thickness. Okay, thickness is thin, okay, or narrow. Okay, this is for high density cells, means that uh, in the chip, there are many cells. Okay, the layers that are used to connect all the transistor or all the cells use this low level layer. Okay, and if we want to connect one module, okay, to another module, maybe a thicker layers should be used. Okay, so here you see the layers of M2 to M4, okay, with thicker layers. Okay, this is called also as wires that has longer length. Okay, this is for longer wire. Okay, if we want to carry current from one terminals to another terminals, okay, we also have to consider the thickness of the layer. Okay, the thickness of the layers will determine the current carrying capacity of that interconnects. Okay, so the higher level of the layers, they should have able to carry larger current, okay, and also over a long distance. Okay, for M5 and M6 layers, this is with a thicker layer, okay, for VDD, ground, and clock. Okay, so different metal layers, they have a different function. Okay, metal layers, okay, to recall, there is a power or ground routing, okay, and also there is a signal routing. Current carrying capacity of a metal wire depends on the cross sections. Okay, cross sections means the area, cross sections area of that metal wire. Okay, cross sections is determined by the width and height. Okay, sorry, width and length. Okay, it should be width and length. Okay, here height is fixed. So width determines the current limit. Okay, the width of the metal layer in this case is important. Okay, it determines the current carrying capacitor of that metal wire. Okay, and metal migrations. Okay, what is meant by metal migrations? When current is too high, electrons flows pushes around metal glands. Higher resistance increases metal migrations, leading to destructions of wire. Okay, this means that a metal interconnect has its maximum limit. Okay, the maximum limits here refers to how large the metal layers can allow the currents to flow through it. Okay, the current carrying capacity of that metal layers, okay, is also determined by the material used. Okay, um, the current, if it is too high, okay, it will cause the destructions of the wire. Okay, uh, why? Because the higher resistance will increases the metal migrations. Okay, so this is the limit, okay, of the metal interconnects. We call it a metal migration. Okay, resistance. Okay, resistance here, there are different sources of resistance. Okay, as you all know, the most transistor, they are drain and source terminals, and also they are wire and also contact. So all these, they cause resistance. Okay, so all the resistance here will be mentioned, okay, one by one. Okay, in general, the source of resistance is from the on resistance. Okay, what is on resistance? It is a resistance that will cause when the transistor is on operation. Okay, and also there is a source and drain resistance, contact resistance, and wiring resistance. Okay, so all these are the source of the resistance in a MOS transistor. Okay, you see the diagram here. Okay, there are source terminals. This is the source diffusion area. Okay, this whole thing. Okay, source diffusion area. Not source diffusion area. It is N plus diffusion area. Okay, uh, it is used as a source terminal. Okay, this is also the same. Okay, okay, and this diffusion area is used as the drain terminal. Okay, so you see here two terminals here, they are with contact. So this is the contact. This is contact. And this is the metal layer. We call it interconnect. Okay, so these metal layers, we usually connect it to VDD or ground. Okay, depending on which this depending on the type of the transistor. If this is a PMOS, then the source will be connected to the VDD, and there will be a current flow, okay, through the terminals, through this terminal, source terminal, to the drain terminal. Okay, if the input voltage is low, okay, we also have to uh, uh, see what is the input to the transistor. For PMOS, if it is a low input voltage, then this PMOS will turn on. Okay, and then you see here, this is the current flow. Okay, the current flow here is actually flow through the channel. Okay, that is underneath the polygate. Okay, okay, and here the current flow through the channels to the drain terminals and to the ground. Okay, if this is connected to the ground. Okay, so here uh, this it shows the current flow, okay, the directions of the current flow, and then with all the resistance that is existed, okay, in this MOS structure. MOS structures resistance, okay, we usually um, will mention it. Will mentions about the resistance of that MOS structures when it is on. Okay, the models, the simplest models, okay, assume for the transistor when it is on, okay, we can use this model. Okay, since transistor is a switch, okay, so we can also draw the transistor in another form, which is as a switch. Okay, this is the switch. Okay, to illustrate a transistor. Okay, and then in a real case, this switch is with an resistant. Okay, this resistant we call it as a finite on resistant. Okay, when the switch is off, there is also a resistant. We call it as infinite off resistant. Okay, so in this slide, I will talk about the on resistant. What is meant by the on resistant here? Okay, the definitions given here is the resistance values between the drain and source of a MOSFET during the operation. Okay, it is defined as RDS on. Okay, DS is the drain and source. Okay, the smaller this value is, the lower the power loss. The power consumed is calculated as RDS on multiplied with the drain current. Okay, the drain current is square. Okay, this is the formulas that is used to calculate the power dissipations. Okay, the values of RDS is on the order of ohm or less. Okay, so the resistance here, as stated, is actually not very high. Okay, it is in ohm. Okay, not kilo ohm, not mega ohm. So still consider small. It is a very small resistance. Okay, and the power consumed is typically lower than a conventional transistor. If the amounts of the heat generated is less, okay, the heat dissipations measure will be easier to implement. Okay, so when we talk about the amount of the power dissipations, okay, it will dissipate as a heat. Okay, so the heat will increase the temperatures in a device. Okay, so the temperature is very critical. Okay, if it is high temperatures, it will damage the device. Generally, the larger the chip size of the MOSFET, the smaller is the on resistance. Okay, as the package size increases, the possible chip size also increases, resulting in lower on resistance. The figure compare the lowest levels of the on resistance for various compact packages. Okay, here is a graph. Okay, not graph, is a chart. Okay, it is a chart that shows the uh, different chip size with different on resistance. Okay, for this you see here, okay, this is the feature size of the chip. Okay, from small to large. Okay, the feature size, and then here this is the on resistance, the ohm, RDS on. Okay, smaller chip, okay, will have a larger RDS. Okay, this is a larger chip size, have a smaller RDS. Okay, this graph I picked from this website. Okay, this is the website which you can refer to. Okay, the contents here is actually I get from this website. Okay, to show you how the chip size, okay, affect the smaller RDS. Okay, the graph have already shown that. Okay, source and drain resistance. Okay, just now talk about the on resistance. Now is the source and drain resistance. Okay, source and drain resistance will refer to this resistance. Okay, that is at the terminal. Okay, and terminal here, the source and drain terminal, they are formed by the diffusions. They are formed by diffusing the dopant on the substrate. Okay, this is the source terminal. Okay, this is a drain terminal. Okay, this diagram didn't show any diffusion area. Okay, but we straight away should know there is a diffusion area if we draw it in another diagram, which is a physical diagram. Okay, in 3D. Okay, so there is a diffusion area. So you see here, this is another diagram. Okay, with a diffusion area, this is source or drain terminal. Okay, this diffusion area, if you want to form a diffusion region, okay, we have to dope it. Okay, dope with the dopant. Okay, dopant here is a N plus N-type dopant. Okay, N-type dopant. Okay, so the N-type dopant can give some resistance. Okay, can give some resistance. The resistance here we call it as the sheet resistance. This is S. Okay, sheet resistance. You will see sheet resistance is defined as RS or R. This is I don't know what it is called as, but we usually call this as a sheet resistance. Okay, so you see here, this is the sheet resistance. Okay, sheet resistance multiplied with the length and the width. Okay, we'll get the source resistance or the drain resistance. Okay, the length and the width here is the length of the source and drain diffusion area. Okay, and then the sheet resistance of the source or drain diffusions will range from 20 to 100 ohm. Okay, the values here will change. Okay, it will change depends on the material used. Vary based on the material. Okay, vary based on the material. The shallow diffusion region under the dielectric spacer is a contributor to the parasitic resistance. Okay, the shallow diffusions here have to refer to this diagram. Okay, it is actually refer to this one. Okay, according to my understanding, if I'm not mistaken. Okay, the shallow diffusion region under the dielectric spacer. Okay, refer to this. Okay, this is a shallow region if compared to the region here. Okay, so I will refer to this shallow diffusion area. Okay, so this shallow diffusion area, okay, will cause a parasitic, okay, to the this device. Okay, you see here, it will contribute to the parasitic resistance. Okay, and the shallow junction is needed to prevent excessive off-state linkage as in short channel transistors. With a silitations, the silicide, okay, this is the silicide, okay, with different material used, okay. It can reduce the sheet resistivities of the N plus or P plus source and drain regions by factors of 10. Okay, a silicide actually can increase the conductivity. Okay, silicide can increase conductivity. Okay, when the conductivity increase, it means the resistivity is decreased. Okay, it's reduced. Okay, if we want to have a better conductivity in the chip, okay, or in the transistor, we have to make sure that the resistivity is low, okay, and with higher conductivity. Okay, so the silicide here can be used to achieve that. Okay, and also silicide can reduce the contact resistance between the silicide and the N plus or P plus silicon. The contact resistance is another main source of resistance. Okay, the silicide is formed simultaneously by reactions between the metals and silicon at a high temperature. Okay, so now is about the wire resistance. Okay, just now already show you the source and drain resistance. Okay, they are determined through the sheet resistance. Okay, wire resistance also. Okay, it is also determined by this sheet resistance. Okay, this is sheet resistance and the wire resistance. Okay, is determined by the sheet resistance and the length and the width of the metal layer. Okay, the sheet resistance here, okay, as you see here, it can be defined as the resistivity divided by the height. Okay, this is height. Okay, you see here. Okay, the height of the metal layer. Okay, here sometimes the height we also can call it as the thickness. Okay, you must be careful of the term here. Okay, if you are confused, you need to clarify. Okay, the height here also means the thickness of the layer. Okay, two table given here. You see the slide. This is a table that is for the resistivity of different material. Okay. Okay. For metal layers, the materials that are used are copper or aluminum. Okay, and then they are with a certain resistivity. Okay, and then the sheet resistor. Okay. Okay, this is resistivity. The value is constant. Okay, and then the thickness of the layers will change. Okay, the sheet resistance. Okay, we have to consider the sheet resistance. We have to consider the sheet resistance based on the thickness of that metal layer. Okay, as you can see here, this is the table that's given for the sheet resistance for different um, layers or different area. Okay, the material here means the N plus or P plus field diffusions. Okay, and N plus or P plus diffusions, this is for the source and drain terminal. Okay, and this is the source and drain terminal with a silicide and polysilicon with silicide and aluminum. Okay, all the sheet resistance for all these are stated here. Okay, If you can see here, the polysilicon and polysilicon with silicide, when we compare these two, you see the values here are, uh, are different, okay? They are in big difference. The sheet resistance for the polysilicon without silicide is higher, okay, than the polysilicon with silicide. Polysilicon with silicide, the sheet resistance is 4 to 5. Okay, so the resistance is lower. It also means that the resistivity is lower. Okay, the resistivity is lower. Okay, when the resistivity is lower, then the conductivity is higher. Okay, there is a relationship here to relate the conductivity and the resistivity. They are inversely proportional. Okay. Choice of metal. Okay, this is the choice of materials for metal. Okay, until 180 nanometer generation, most wire were aluminium. Modern processors use copper. Okay, the copper atoms diffuse into silicon and damage the fat. Okay, therefore it must be surrounded by a diffusion barrier. Okay, another source of resistance here is the contact resistance. Okay, contact, you know what is contact. Okay, contact itself will also cause resistance. Okay, contact is a transition between the routing layers, okay, through the contacts, okay, through the contacts. And the transitions between the routing layers will add extra resistance to a wire. It keeps the signals wires on a single layers whenever possible, okay, and avoid excess contact. Reduce contact resistance by making the contacts larger. Okay, beware of the current routing that puts a practical limit on the size of the contact, or by using the multiples minimum size contact to make the contact. Okay, type typical contact resistance. Okay, the values should be 5 to 20 ohm for metals or polysilicon to the N plus or B plus diffusions, or from the metals to the polysilicon. Okay, and also the contact resistance for metals to metals layer. This is not layers. The contact from one metals to another metals. The resistance here is 1 to 5 ohm. Okay. Okay, so here conclude that the contact resistance, okay, will be based on the contact size, okay, and the contact must be reduced. Okay, what I mean here is the numbers of the contact must be reduced. Okay, and then more pronounced with scaling since the contact openings are smaller. Overcoming interconnect resistance. Okay, how to overcome the interconnect resistance? There are a few techniques here to overcome the interconnect resistance. Okay, first is to selective technology scaling. Scale the width while holding the thickness constant. Okay, and use a better interconnects material. Okay, the better interconnects material is to use a lower resistivity material. Okay, like copper. Copper is a material that has lower resistivity. And as the processes streak, wire get shorter, but they get closer together. Okay, increasing the capacitance and narrower. Okay, narrower will increasing the resistance. Okay, so the RC wire delay increases and capacitive coupling get worse. copper has about 40% lower resistivity than aluminum. So copper wire can be thinner, reducing the capacitance without increasing the resistance. Okay, so this one think roughly you can understand from these statements here. Okay, it means that if two layers, okay, into interconnect, okay, imagine that this is a metal layer, okay, in a chip that has transistor, many transistor. The numbers of wire will also increase. This is many transistor. The numbers of wire will increase. When the numbers of wire increase, the distance between wire, or okay, I should use spacing instead of distance. This is spacing between wire. Okay, this is spacing. Okay, spacing will be smaller, means the wire get closer. Okay, when the wire get closer, okay, it will increase the capacitance. Okay, as already stated here. Okay, and narrower will increase the resistance. Okay, so when there is two wires, they are very close to each other, it will increase the capacitive capacitance. Okay, this is the capacitive capacitance. Okay, they will be capacitive coupling. Okay, there will be capacitive coupling across each of the wire here. Okay, and then both of the coupling that occurs in the two wires here, they will cause increasing capacitance. We call it as capacitive capacitance. Okay, and other than use a lower resistivity material, okay, another technique is to use a silicide. Okay, this one already mentioned just now. Okay, using the silicide, the conductivity is 8 to 10 times better than alone. Okay, and the last one is to use more interconnect layers. Okay, more interconnect layers is to reduce the average wire length L. Okay, but beware of the extra contact. Okay, this is by condition. Okay, use more interconnect layers is by condition. Okay, it doesn't really means that more interconnect layers will be better. Okay, we also have to consider the spacing between between all the wires. Okay, between the wires. Okay, we have to make sure that the wires are not too close to each other, and at the same time we have to consider the wire length and the number of use of the contact. Okay, we have to try to reduce the numbers of contact use. Okay, because contact will cause resistance as well. Okay, so that is all about the resistance that we have to consider in a most transistors. Okay, uh, so there are four. Okay, four resistance. So all the four resistance you will have to understand. Okay, and skin effect. Okay, skin effect. What is meant by skin effect here? Okay. The metal layers that is used to carry current. Okay. They are also apply with frequency. Okay. When there is a current, of course, there is voltage drop. Okay, or voltage. Okay, and uh, current and voltage here. Okay, they can be in AC. Okay, it can be in AC, not DC. Okay, so it will the currents flow through the metal layers. Okay, will be different at different frequency. Okay, at low frequency, most of the copper conductor cross sections carry current. Okay, so this is a conductor. Imagine that this is an isolated conductor. Okay, apply with a low frequency, and then this conductor here illustrate that the whole cross sections of the conductor carry the current. Okay, at high frequency, currents tend to flow primarily on the surface of a conductor, with the current density falling off exponentially with depth into the wire. Okay, so this is a wire that carry current at high frequency. Okay, so currents tends to flow on the surface. Okay, so this is the surface. Okay, the conductor, the surface of the conductor, with all the with highest current density. Okay, okay, and then the current density decrease with the depth. Okay, into the wire. So you see here, this is current. Okay, as a highlight here, the density here is higher. Okay, and then the current density drop. Okay, when the depth of the wire when is increased. Okay, so here the density drop, the current density drop. Okay, with the depth of the wire. Okay, the density of alternating current to concentrate near the surface of conductor is known as the skin effect. Okay, so this phenomenon we call it as a skin effect. Okay, it is occur only when there is an alternating current. The resistance of the conductor is slightly increased when carrying an alternating current. Skin depth is a depth at which the conductor current is reduced to 37% of the surface value. And this is the formula, okay, that can determine the skin depth. Okay, it is determined, okay, by using some of the parameters here. Okay, skin depth is influenced by the frequency, okay, signal frequency, wire conductivity, and the magnetic permeability. Okay, effect on resistance. Okay, this is mean the skin effect on the resistance. Okay, at low frequency and high frequency. Okay, just now mentions skin effect only occur at high frequency. Okay, and then if we use different frequency, low and high frequency, the resistance of the wire will also be different. Okay, so for low frequency resistance of wire, okay, it is evaluated as RDC equals to 1 over the conductivity of the wire multiplied with the width and the thickness of the wire. Okay, And the high frequency resistance with skin effect, okay, is given by this one. We can use these formulas to determine the high frequency resistance. And the resistance per unit length, this is the formula, okay. So this formula, okay, all this formula is for your reference, okay. You no need to memorize. This is to show you that the resistance varies from low to high frequency. Okay, here is a formula shows the conductivity and the resistivity. Okay. Okay, skin effect for different width. Okay, the frequency here is plot. Okay. Okay, this graph shows the increase in resistance versus the frequency. Okay, so when the higher frequency use, it will cause some significant increase in the resistor. Okay, this is the resistance. Okay, and the increase of the resistance here also will be different. Okay, for different width. Okay, this is the width of the layers. Width of layer. Okay, if we see this graph, if the width of the layer is small, okay, or the layer is narrow, okay, it seems that the resistance here, okay, is lower. Okay, is lower when a higher frequency is applied. Okay, if we compare, okay, at this point, okay, I use 1 point here. Okay, at this point, you can compare it easily. Okay, for the width of layers that is small, the resistance are smaller. Okay, this is the resistance. Okay, at this frequency. Okay, this frequency, okay, you know what is the value. It is between the 1 power 10, 1 multiplied 10 power of 9, okay, in between, okay, this value, okay, 1 multiplied 10 power of 9 to 1 multiplied 10 power of 10. Okay, so for larger the width of the wire, larger width, okay, it shows that the resistance of that wire increases, okay, at a constant high frequency. Okay, so here we can know that the width of the wire, we must make sure that is smaller, okay, must be made smaller. Okay, a 30% increase in resistance is observed for 20 micrometer aluminum wire at 1 gigahertz. Okay, versus only a 1% increase for 1 micrometer wire. Okay, so this one is referred to this one. Okay, already draw here. Okay, this is 1 gigahertz. Okay. Okay, I think I will stop here. Okay, I see that the time is almost near to the our class is until 11:30. Okay, I will cover the capacitance in this coming Wednesday. Okay, one student absent. I see here. Total is 28. So I received all the forms from you. Okay, no issue on your attendance form. Okay, we can dismiss class now if no further questions. Okay, I will see you on Wednesday. Okay, thank you. Okay, some students have to stay back because we still have another tutorial class.